Hello and welcome. Today we're tackling one of those classic Python puzzles. It's a real head scratcher, something that trips up even experienced developers, especially if they're coming from another language. We're going to solve the mystery of how Python really passes arguments to functions.
So if you've spent any time with languages like C++ or Java, you've been trained to ask this exact question, right? When you call a function, are you sending a copy of your data, or are you sending a direct link to the original thing? It seems like it should be one or the other. And here's the big twist. With Python, the answer is neither. It doesn't really fit into either of those neat little boxes. Python does its own unique thing, and once you get it, it'll completely change how you understand your code.
So here's our game plan. We'll start by defining Python's unique approach. Then we'll introduce this super helpful mental model. Think sticky notes. After that, we'll dig into the huge difference between mutable and immutable objects, see it all play out with real code, and then wrap up by talking about what it all means for performance versus keeping your data safe. All right, let's dive right in. So, if it's not passed by value and it's not passed by reference, what on earth is it called? Well, Python actually has its own special name for this whole process.
It's officially called call by object reference. And the key idea here is that when you call a function, you're not passing the data itself, and you're not passing a raw memory address. What you're really passing is a reference, a pointer basically, to the object that holds the data. That distinction is super important. It's the key to this whole thing. Okay, to really make this concept stick, we've got to throw out our old ways of thinking and grab onto a new one. I'm telling you, this is the single most important idea for understanding how Python variables actually work.
First things first, you have to stop thinking of a variable as a box or a bucket that you pour data into. I know, a lot of other languages work that way, but in Python, that mental model will lead you down the wrong path every single time. So let's just toss that idea right out the window. Instead, I want you to start thinking of variables as simple name tags, or maybe even better, sticky notes. The real data, the number 10 or a list like 1, 2, 3, those are the objects, and they're just kind of floating around in your computer's memory. Your variables are just labels that you stick onto those objects. You can even have multiple sticky notes stuck to the very same object. Okay, now for the next piece of the puzzle. Now that we know variables are just sticky notes, how a function behaves depends entirely on the type of object that sticky note is attached to. See, objects in Python basically fall into two camps. On one side, you have immutable or unchangeable objects. Think numbers, strings, tuples. Once you make one, it's set in stone. You can't alter it. On the other side, you have mutable or changeable objects. These are your lists, dictionaries, and sets. You can actually reach inside these and change their contents around. This difference is absolutely crucial. All right, enough theory. Let's see how our whole sticky note idea actually plays out with some real Python code. This is where it's all going to click. So let's start with an immutable object, like a simple integer. Because you literally can't change an immutable object, when you try to modify it inside a function, Python's behavior ends up looking a whole lot like pass by value. Okay, let's trace exactly what's happening. Outside our function, we have a sticky note called num, and we've stuck it on the number object 10. Then we call the function. Python creates a new local sticky note called number, and sticks it on that very same 10 object. But then, the moment we try to add 1 to it, Python has a problem. It can't change the object 10. So what does it do? It creates a brand new object, 11, and moves the local number sticky note over to it. And the original num sticky note, it never moved an inch. It's still pointing right back at that original 10. So what about mutable objects, like a list? Well, because we can change these objects without creating new ones, the behavior looks a whole lot more like the traditional pass-by reference you might be used to. Now, this just illustrates the difference perfectly. We start with our sticky note, mylist, pointing to the list 1, 2. Inside the function, another sticky note, items, gets stuck to that exact same list. But this time, when we call .append 3, we're not moving any sticky notes. We're reaching into the object that both notes are stuck to and changing its contents. Since both mylist and items point to that one single shared object, the change is visible from everywhere. The original list has been modified. But hold on, there's a classic gotcha here. What happens if you're inside that function with your list, but instead of modifying it with something like .append, you use the equal sign to assign it to a totally new list? And this is the part you really have to remember. The equal sign is the great separator. The moment you use equals on that local items variable, you're telling Python, hey, rip this sticky note off whatever it's on right now and stick it onto this brand new list I just made. The link to the original object is completely broken. And your original my list? It's totally unaffected, still pointing happily to its original data.
So now that we get the mechanics, what does all this mean for us when we're actually writing code? This isn't just some academic puzzle, you know? It actually forces us to make real decisions about how we design our functions.
It really all boils down to a trade-off. Let's say you're working with a massive data set, a list with millions of items. Modifying it in place like we saw is incredibly efficient. It saves a ton of memory and time. But if data integrity is your absolute top priority, and you absolutely cannot risk some function accidentally changing your original data, then you've got to be a lot more careful.
So how do you program defensively? Well, for starters, you could just use an immutable type, like a tuple, from the get-go. Or if you have to use a list, you can explicitly tell Python to pass a copy of it by using .copy. This gives the function its very own duplicate to mess with, leaving your original data perfectly safe and sound.
So the next time you write a function in Python, just take a second to think. You now have the right mental model to know exactly what's happening under the hood. The only question left is, for this particular job, are you going to prioritize the raw speed of changing an object in place or the absolute safety of knowing your original data is untouchable? The choice is yours.